beverages later?
Yeah, I'll be around.
Awesome. So if you think of more questions, you can find Matt later. And then MCFSTR on all of the things. And next we have Ben Volpace telling us about Hive, which allows Lisp in Python, right? Yes. Awesome. Oh, also, there's still more pizza from Reply, and our lovely co-organizer Joe went and got us more cups. So now everybody gets water. Thank you, Joe. And there's also gluten-free and vegan pizza over here as well. If you need some special things, there are special things for you. So please eat. Enjoy.
What else? Yeah. I know some Lispers who use Vim. Always close. So close. So close. So close. So it looks like we've hit at least 2% remaining in the queue. It's an engineering rounding error. Hi, I'm Ben. Benjamin Volpace. I'm Ben K. I'm only on IRC. I do backends, infrastructure. I love Bitcoin. I think it's really cool. I probably know more about Bitcoin than anybody except the core dev team at this point. And judging from some of their commits, I might know more than some of them too. I like Lisp. And my firm tries to situate ourselves at the intersections of business, engineering, and design. What's High? High is not production ready. It's a baby Lisp. It's still in production, or it's still in its massive phases. So how do you get one of these? Well, you brew install everything. You make a new High, a new virtual env just to play with High. You activate it, and then you actually clone the latest High laying down because it's changing very quickly and it'll move out from underneath PyPy pretty quickly. So I just recommend getting the source. Setup.py, install that. I know nobody does that anymore. And then instead of running Python, you actually run High itself. And you can do cool things like add stuff, which is pretty neat. The basics of High, I'll walk you through this. You can add stuff. And the difference that you'll notice here, if you're mostly a Python person, is that this is prefix notation. So you're putting your operator at the front of all of your expressions. And a lot of the expressions you'll see are multi-arity, meaning they'll take a bunch of different arguments. You can take many different arguments. So this is an example of using the addition operator to add several things together. When normally in some other languages you'd see something more along the lines of 1 plus 2 plus 3. In High, in other Lisps, it'll do plus 1, 2, 3. Subtraction, same story. Walk it back down. You can do cool stuff. You can nest functions. So this is subtracting this function here, the sum of 1 and 2, from the sum of 2 and 1, and that'll give you 0, unsurprisingly. Defining functions is fun. Oh man. There we go. So it's pretty terse. You just define the name of your function, the arguments that you're going to have there, and then you call it. Some other function examples. One of the things that I really like about Lisp is that you start to grow the domain-specific language for whatever problem you're attacking without a lot of boilerplate and a lot of overhead. So if I were going to be doing a lot of squaring numbers and taking square roots, I might come up with helper functions instead of calling the base methods on a regular basis and passing in all the arguments. So in this case, I just want the square, right? So in Python, we exponentiate. This is an example of using some native Python functions. So this takes the exponentiation function and just calls it twice with number. And I call it square. Call square, returns 4. You can do the same thing with square roots. I don't know why I didn't include the source for this one. But this would be something along the line of define square root right, and then you call it, and it takes the square root of whatever you're putting in. And it's pretty smart, I think, because of the Python base layer that's there about coercing things appropriately. I'll have to back out because I actually deleted the rest of my talk. Right there. You can compose functions, which is pretty neat. So the previous function that I defined, add2, I can use that in this function, add4, and it starts off with add2. So we take this added right here, and it gets dumped in here. We first call this function. The way Lisp works is it evaluates your innermost functions first and your outermost functions, and then it goes until you're done. So in this case, it adds 2 to whatever number we pass in, and then adds 2 to that. So we can have add 4 to 4, gives us 8. My cursor even all showing up? That's all right. You can get at all of the native Python stuff. The max of a list of range 10 is going to give you 9. The min of that list is going to give you 0. You can take types of things. So the class of that square root is going to be a float. I doubt that I could get it to put out an int. In my brief hacking at it, I didn't get it to put out an int. So I don't know what I'd need to constrain types there. You can also take the type of a range function, which gives you the class range. I'm not really a Python guy, so I have no idea what that means. But I am a Lisp guy, and there are really cool things that you can do in Lisp. The canonical thing to do in Lisp is the Fibonacci program, or the Fibonacci calculations. And in a scroll. So in a mathy perspective, what is the Fibonacci number? Well, it's the number that is the sum of the previous number in the list and the number before that in the list. So it assumes a list that you've been keeping track of, and each successive element in the list is the sum of the previous two before that. So in pseudocode, that's the current is equal to the previous plus the one before that. And in Lisp, it's pretty concise. So here I'm requiring hi.contrib.loop, which is a set of macros that lets you do cool recursive stuff. And here I declare a function called Fibonacci number, fibnum. It takes one argument, n, and then I call this function loop. And what loop does is it sets up a recursion point. So down here, I call recur, and that's what kicks off the recursion. This is where the function is going to return to. The way it's structured is that each of these terms in here is bound with each of these at the start of the function call. So I is bound to n initially, previous value is bound to 0 initially, the current value is bound to 1 initially. When we get all the way down to the end of the function, I recur and I say decrement I. So next time we come around, I is going to be reduced by 1. We're going to stick the current number in at the previous position, and then we're going to take the sum of the current number and the previous number and recur with that as our current number. So that's kind of crazy. It can be hard to wrap your head around that all at once. So I've come up with some examples of how this works. You can do this again and again and again. with take 10, or take n, really. And that'll return a generator itself, which is pretty cool. Very cool. And then you coerce that to a list by calling list on it. You can also simply call nth on it and get the nth Fibonacci number in there. That's all pretty cool stuff. I find that pretty cool. Mapping is another cool Lispy thing that we can do. Hang on, I want to collapse this. Mapping takes one function and then a list of other things and applies that function to each of those items in the list. It's really useful. I don't know how many times you have dealt with lists in your programming career, but having a set of functions like in the Python functional programming set of functions that do all of this mapping and reducing as well is really useful. So some examples. If I just want to map an addition function across a list of things, I can call @map, the function that I'm interested in, and then a list of things. And wouldn't you know, that returns a generator object in its memory address. But what I really want is I want the list of those things. So as before, when I was just calling that Fibonacci sequence, or that Fibonacci number, I would have gotten a generator back had I not called the list function as well. And that's what I'm demonstrating here, is that you call list, and it gives you the list of the result of applying this function, of mapping this function across all of those items in the list. Here's an example of mapping the Fibonacci number sequence that I came across. Oh, I forgot to mention, it is the special variable that gets bound in these mapping functions. So if you have a function that takes a single variable as its argument, that's how you curry those values in. So there's the generator object I was talking about. Here's how you get the list out of all of them. And you can get crazy numbers out of it. It's Fibonacci. What was I trying to demonstrate here? That, it's just different ways of going about it. You can put in random numbers, you can, compose it with other functions. So range itself returns a generator, right? So you can stick that generator in as the list that you're interested in, and then map whatever function you're interested in across that. So I wrote the Fibonacci number generator, which is a useful thing. But then my boss came back to me and said, I really want a whole list of Fibonacci numbers. I don't really want to rewrite that. So what I'm going to do is I'm going to write a new function that returns the list that results from mapping the Fibonacci number across however many numbers I provide there, which is pretty cool. You can imagine it gets pretty computationally intense. I think it's like an O squared, but I'm not a computer science guy, so I wouldn't know. But fibseq of 2 gives you the right sequence, 1, 1. 4 gives you 1, 1, 2, 3, 10, and so on. And at 100, they start to take a little bit of time. At 1,000, I think it actually eventually completed, but I had to wait a while. Try it yourself. We can also get infinite sequences, which is a really cool thing. If you've ever done Taylor expansions or any of the calculus stuff, there's a lot of use in having infinite sequences at your fingertips. You can make really interesting estimations of stuff with infinite sequences. So this is shamelessly stolen from the Hi demo itself. And the way this one works is we set a variable a to 0, we set a variable b to 1, and then while true, we yield a, and then set the variables a and b to b and a plus b. So it's a much more concise rendering of the function that I wrote before, without recursion. And this one runs as a loop. This gets reduced to a generator in Python, which is cool because then you can take 10 of them. And you can have this infinite sequence, and take as few or as many as you want, all the way out into space, without consuming too much by way of resources. Macros are crazy, so I'm not really going to get into them here, but I'll give you a little bit of a walkthrough of how macros work in Lisp. We define a reader function, and what this is doing is this is sitting inside the language, and it's giving you new tools to rewrite your language as you play around with it. So I'm defining a new reader macro, t, and what t does is it takes the expression and it splices it in there, and then it unquotes it. So this is the splice operator. It says, take whatever expression was passed in and put it inside this function here, this part of the S expressions. And then this right here says, pull it out of any surrounding parentheses or list object that it would have and drop it into, right here, this list object, this list. This comma right here is how we indicate that this is going to be a list. It could also just be this, it's just shorthand. And this right here quotes it so that it's not evaluated. You'll notice in some of these, that the first first thing in a list when evaluated at the REPL or in your code is going to be the function that gets called. Now here, I don't want this function to get called, so I'm quoting the list, saying don't evaluate it, just pass it on to whatever gets called next. And then I call the reader function, that's the shorthand for the reader function, it says get this reader function t and supply it this list right here as its argument, and it returns this. You can do crazy stuff with this in Lisp. If you have a library that you really, really like, and one part of it isn't working very well for you, or you see a use over there for a set of functions in that library that just need some swapping around internally, they're just lists internally. It's just a nested list internally. So you can take it, munge it around in your code, re-render it over there, change it around in such a way that it takes the arguments that you expect to see and does the things that you expect it to do. They're dangerous though. They're very hard to debug and also very hard to explain to other people on your team. Might have something to do with why there's not a lot of Lisp in production. So a little bit of philosophy, if nobody minds. Why Lisp? Well, as I mentioned before, you're going to run into a lot of lists. I have run into a lot of lists. When all of your tools are oriented around lists, it just drives you to thinking about everything in terms of lists and working on them that way, which is really nice. There's a lot of reduction in mental overhead compared to other languages that I've worked in, other dialects that I've worked in. Not a lot of, instantiating a thing, passing it some arguments, wondering about what its state is, moving it around. There's a simplicity that comes with Lisp. And a real extreme flexibility in shaping the language to the problem domain. I've found this again and again and again, that I don't really want to be spending a lot of time cooking up a whole set of classes and encapsulating details about my program and its execution environment and the problem I'm trying to deal with. I just define a function that does a simple thing, or parses a simple set of data and returns me the things that I'm interested in. And I compose them. I take functions that I've already written, and I include them in other functions that give me really specifically what I'm looking for. And that extends to your abstractions as well. So not just the functions themselves composing, but also your abstractions start to compose as well. And Lisp has a habit over the years of selectively absorbing really good ideas from the programming mainstream. Not universally, right? Like there are many dialects of Lisp out there, and some of them move more quickly in absorbing stuff, and some of them make more rigorous, posts in the sand about what's going to get included and what's not. A good example is one of my favorite languages, Clojure, has a lot of really good concurrency and parallelism primitives, because that was the set of problems that its designer was struggling with when he cooked up that language. But why not Lisp? Well, you may develop job dissatisfaction because it's so simple and other things make life so complicated. I suffer from job dissatisfaction. There's a perennial toolchain problem. Are you going to use Emacs? Are you going to use Vim? Are you going to use an IDE? Are you going to use some crazy thing that some person has thought up in the past couple of years that has not too much support for a whole bunch of stuff? Debugging, refactoring, like you don't get all of your really hammered on tools the way you do with like Java or even Python. The best that I've been able to find is Emacs, and it takes a lot of work to get Emacs to work for you instead of slowing you down. That's an investment that you make if you want to work with these sorts of things, I think. It can be damn hard to find Lisp work. I use it for all of my personal projects, all of my client projects where there's backends that don't need a whole lot of complexity. But it can be really hard to find good places where it's a good fit. And you may become a grouchy old person with bizarre notions about technology. Because a lot of these ideas have been around for like 30 or 40 years, especially in terms of the simplicity of stuff. And you might find yourself asking questions that are very hard to answer about why the world is the way it is right now. What went wrong? Anyways, that's my talk on Hi and Lisp. Thank you for your time. Questions?
So is the reason you're using recur and appmap because they return generators as opposed to like actually calling the function again? Because like I noticed in your Fibonacci recursive example, you're using some kind of recur thing that you imported from a Hi.
Sure. So what would the alternative be there?
Just to call the function again, like to put in the function name and just keep going instead of this recur. Like I don't know.
Because I don't know how to set up. Because if you just call fibnum again,
Yeah.
You're only going to pass in n, and so you have to maintain state in here.
Oh, okay.
Call fibnum twice, right?
So again,
Call fibnum twice, once with n minus 1, once with n minus 2.
you could.
It happens.
You could. That's a way to factor it.
I mean, if I was going to do this in Erlang, I'd define like a fibnum 1 and then have it, tail recursive state to the rest.
Yeah. Also hacked together over the course of just a few days.
Yeah, so I'm super interested about Python interrupt. So it's cool that there's Lisp in Python, but there's lots of other Lisps. Like, can I actually use other Python libraries?
Yes, you can. If you check the Hi documentation, you can see how to build a Django app with Hi.
Right. Yeah.
It turns all of your normal function calls into all of your like change dot, and then the parens into.
It like inverts like dot calls on.
Yeah, it's more like, I don't remember the exact syntax, but it's like, I've been spending a lot of time in Java lately, so like integer, big int, 2, that sort of thing, and like, I don't know. That's not a really great example, but like, I don't know, imagine there's a, odds, dot. So like, imagine that odds is a built-in that only returns odd values. That's the basic format. Their writing philosophy is, when in doubt, defer to closure. If closure doesn't have a good example, Common Lisp.
Right.
And Common Lisp doesn't have interop on a host platform. Anybody else? Thank you all for your time.